Hello wonderful person, this is Anton, and in today's video we're actually going to be discussing pulsars and neutron stars. And as you can probably tell from the title, we're actually going to be discussing their death. We're going to talk about 3 hypothetical situations when these beautiful objects can actually disappear or turn into something else. Anyway, welcome to What the Math. So in case you don't actually know what a pulsar or a neutron star is, you may want to check out some of the previous videos where I discuss basically their nature and the idea behind them. But long story short, it's basically a relatively small remainder of a star that used to be relatively massive, that then has become a very compact, very dense object, theoretically known as a neutron star, but in practicality it's a little bit more complex than that. The size of this particular object is about 12 to possibly 18 kilometers in radius. Basically, it's the size of a relatively large city, with a mass of 1.8 masses of the Sun. It's basically if you took a lot of mass and condensed it into a small, very, very small object. Now, we've talked about white dwarfs, and we've also talked about their potential demise and how they disappeared, but we've never really talked about the neutron stars. Let's actually see if we can maybe just go into a new simulation here and create a neutron star that's not a pulsar. Or actually just pick one that already exists in real life. We might even go with one of the more famous ones, the Crab pulsar. Or I guess you can call it Crab neutron star. So this object right here is located in the very close to Orion Nebula. And it's one of the most famous neutron stars we currently know. The mass here is 1.4 masses of Sun, and the total radius is about 11.5 kilometers. And if you were to look at the structure of this object, so this is what you would discover. There's actually 4 specific areas, with essentially 5th being the atmosphere. And for this reason, it's more appropriate to refer to a neutron star as actually a neutron planet, because they are more planetary than star-like. But basically you have the atmosphere on the surface, and this atmosphere is extremely hot. It's basically all plasma, but it is there, and it's about 2 to maybe 3 centimeters in height. That's right, centimeters. It's basically like an inch of atmosphere. Then there is something called outer crust, and this is essentially a relatively hard surface-like structure, similar to, I guess, what we have on Earth, similar to, in a sense at least, a somewhat hard shell that you could kind of refer to as a lattice, but this lattice is made out of mostly electrons and a lot of highly dense ions. So basically it's a mixture of different molecules. So it's not really neutrons. The neutrons come a little bit further down. They do start with inner crust, but inner crust is actually more fluid, and it's actually superfluid. It's a fluid that acts in a very, very unusual way. And this superfluid layer is made up of neutrons, electrons, and also some ions as well. Then outer core, even deeper, this is actually at a depth of about 7 kilometers, is essentially mostly nuclear matter. So here you have a lot of neutrons, but also some protons, some electrons, and it is also superfluid. And lastly, you have inner core, and this is where we don't really know much about, but it's definitely not neutrons. It's probably subatomic particles like quarks and a lot of other unusual but super dense and super hot matter. So this is what a neutron star is like in a nutshell. So how does it actually die? How can this very unusual object basically disappear? Well, there's at least 3 ways. And one of these ways is actually if it has a partner. So here, this is something we've been able to detect in real life as well with a very recent discovery of our neutron star collision. But if I were to basically place another Crab pulsar right next to this one, they would basically disappear. But here what you see is essentially a supernova. And this is exactly what we saw. We saw a very, very powerful supernova, more commonly referred to as a kilonova, that often occurs if a pulsar has a partner that it collides with. So we're going to actually do this a little bit slower just so you can see what actually happened. And basically this is when a lot of more exotic metals and a lot of other matter is actually created. They are created when a neutron star essentially explodes and releases a tremendous amount of materials. So let's see if this is maybe a little bit better. Nope, still too fast. And unfortunately, because they are so small and so massive and dense, it sort of happens almost right away. So the collision here is almost immediate. So anyway, so that's what you'd expect from two neutron stars colliding with each other. They basically create a supernova, and what's left behind is usually a black hole. Now, this is something that we've observed, and we know this is actually does happen, but we haven't observed other ways for neutron stars today. All neutron stars, and by definition all pulsars, have a limit, a mass limit. Specifically here, we're referring to a limit known as Tolman-Oppenheimer-Volkov limit, and this actually refers to the maximum amount of mass that they can have before they essentially just collapse and turn into a black hole. Most recently, we discovered that this mass is actually approximately 2.17 masses of the Sun. In the game, though, it's actually higher. So here I'll have to go much, much higher before we turn this into a black hole. Now, because we know that this limit exists, this also suggests that there are ways for neutron stars to actually gain that mass, and normally this is through absorption of matter from another companion, normally some kind of a white dwarf or even just a regular star. And if they actually accrete enough matter, so we're gonna try to see if we can create this here. So let's see if we can maybe make an object here that starts orbiting the Crab pulsar and possibly collides with it. But basically, if it accretes enough matter, it will eventually, and there's that matter coming, it will eventually reach the limit and then collapse into a black hole. Or, in this particular game, it just turns into a weird object. But anyway, so by definition, once it reaches the limit, it essentially collapses and becomes a black hole. And this will usually happen if it basically absorbs enough matter from a partner, from another object that moves around it. And here you go, here's that black hole. Very, very beautiful, as a matter of fact. We were able to create a very beautiful black hole due to the collisions that this object experienced. And so here, you can actually find these types of pulsars by looking at how fast they pulsate, because as they absorb matter, they actually start spinning faster and faster and faster. And the faster a pulsar spins, the more likely it's going to actually release even more energy, and so it's easier to detect. And in this particular case, this pulsar would have been actually detectable before it creates this black hole, because it would be releasing some of the highest energy particles with basically the fastest possible frequency. So this is the second way it can essentially turn into a black hole or disappear, and that basically means consuming enough matter from the outside. And in this case, we actually created a black hole that seems to even have some sort of a magnetic field, which is pretty interesting. But there's actually another way for a neutron star to get to the same sort of situation where it becomes a black hole through mass absorption, and that's if it was originally born as a neutron star that was already past the limit. Now, how is that possible? Well, there are certain situations when a star, like for example Rigel, might go supernova, and we're gonna do this right now, and leave behind a neutron star that's actually over the limit. Now, in this case, it would turn into a black hole, which it shouldn't have, but there might be a situation where it basically creates a neutron star that's approximately 2.2 or 2.5 or maybe even 3 masses of the Sun, which is past the limit. Now, when that happens, there's a way for it to stay as a neutron star, and you can actually see right now. If it spins fast enough, if it's actually spinning really, really fast, some of the external forces due to the spin are creating centrifugal acceleration. And the centrifugal acceleration prevents the neutron star from collapsing. But with time, though, as it gets older and older and older, due to various events, like for example star quakes that are very, very common on neutron stars, it will actually slow down its rotation. It will stop spinning as fast, and as it stops spinning, the centrifugal force decreases, starts squeezing onto the surface more and more, and eventually, as it basically stops spinning almost completely, it collapses and becomes, once again, a black hole. So that's essentially how it can disappear. And then there's actually one last third way for it to basically become something else. And we don't actually know much about this just yet because it's still very theoretical. But hypothetically, a neutron star, especially when it's really old and when it's already stopped spinning, and when it basically approaches the age of maybe the end of the universe, I guess, basically billions and trillions of years in the future, is going to cool down. And as it cools down, it's also going to start experiencing a lot of really unusual quantum effects, where even though it has a really, really high gravitational field, some of the neutrons might actually get enough energy to be kicked higher into the upper atmosphere, and at this point they might actually decay back into protons and also electrons, and what they'll create is an electron and an antineutrino. Now, basically, they'll kind of evaporate, very similar to how black holes evaporate based on the principle of Hawking radiation. A neutron star might also evaporate based on, well, it doesn't really have a name yet because we haven't really studied it in a lot of detail, but I guess the neutrino radiation. And it essentially starts slowly, very, very slowly decreasing in mass. And at some point, when it reaches, once again, a limit, we don't really know where this limit is, but it might reach a limit where it can't really hold itself together anymore. And when it does that, it will most likely undergo a supernova and just explode, essentially. It's not going to collapse into a black hole, and it's really not going to become a white dwarf, but it will most likely just explode. Now, this we haven't really seen in real life yet, and probably won't, because it's going to only happen trillions of years in the future. But it's a theoretical concept that might occur. So these are the three main ways for neutron stars to essentially die. So either acquiring enough mass and becoming a black hole, losing mass and exploding, or colliding with another object and exploding. All in all, we don't really know much about neutron stars just yet, but there is a lot of speculations about them and a lot of really interesting books as well, including one that I mentioned previously that talks about potential life, a neutron star life, that becomes so super intelligent that basically saves humanity, or tries to save humanity. I don't really remember the story, but if you do want to check out this book, I believe it's called Dragon's Egg. It's actually a relatively old book that you can find in most bookstores. Anyway, that's all I wanted to talk about in this video, and hopefully you learned something from this video as well. And if you did, don't forget to subscribe, share this video with someone who enjoys learning through video games, and come back tomorrow to learn something else. I'll see you guys tomorrow, space out, and as always, bye bye.